vertical coupling into a photonic crystal waveguide using band folding. This work is part of the project to fabricate a fully integrated mid-infrared sensor based on absorption spectroscopy. Because of the unique properties of photonic crystal waveguides, such as low loss at sharp bending and low group velocity, which enhance effective interaction among the radiation and analyte, photonic crystal is chosen as a detection area for this work to have a robust and compact sensor. In spite of the fact that photonic crystal has many advantages, coupling external light into a photonic crystal is a great problem. There are several methods such as coupling through a photonic crystal taper to couple light to this device, which has already been studied in our group. Yet we decided to study a new concept of coupling light to a photonic crystal waveguide using band folding design. In a photonic crystal waveguide, states that who are below the light line are very well confined into the photonic crystal area, therefore they have low loss and high Q factor. However, coupling light through the free space only limited to modes that who are above the light line. The idea is to fold back this mode in above the light line by introducing a double period into the structure. In this work, photonic crystal composed of silicon pillars in air. Waveguide is created by reducing pillar diameter in one row. Red point in this plot present dispersion diagram of a photonic crystal waveguide. Modes who are below the light line are very well confined into the photonic crystal area, therefore they had a high Q factor. However, modes who are above the light line, like this mode, are not very well confined and has a lower Q factor. By superimposing a double period into the photonic crystal structure in X direction, that is propagation direction, the states in this dispersion diagram are folded back with respect to K half into the first half of the reference zone, and we have a replica of them here. As you can see, profile of this mode that is above the light line is similar with the mode that was below the light line. It means that it maintains the properties of the mode. In real structure, introducing a second period can be done by changing diameter of every other pillars in the waveguide area. In addition, we can open some such extra band gap into our photonic crystal waveguide. As already mentioned, we expect to have a high Q for this folded back mode. To study this fact, we use FDTD method. Blue line shows the dispersion diagram of a photonic crystal waveguide with unit cell has the size of one period in propagation direction. Dashed line shows the dispersion diagram for a unit cell that has double period in the propagation direction. As you can see in this plot here, these modes that are the replica of the mode below the light line still have a high Q factor and maintain the property of the photonic crystal waveguide. Other advantage of using this method is one can couple light to many waveguides simultaneously with a high density. This study continued to do a 3D calculation on a structure that is a hybrid system of a photonic crystal waveguide and surface plus one polariton. The reason for this waveguide explained in this work, and a study shows that a proof of the replica of the mode in the above the light line of the brilliant zone. If you are interested to see more interesting results based on the FDTD and RCWA for folding back concept, please visit our poster. Thank you.